Section 1.3. Let A and B be sets. A relation R from A to B is a subset of A cross B given an ordered pair x comma y in A cross B. X is related to y by R written x r y if and only if the ordered pair x comma y is in R. The set A is called the domain, which is going to be the arbitrary point x of R, and the set B is called the codomain, arbitrary point y. And so all that really means is, so we're going to have this notation that we're going to use, and it's just saying that we're going to have an ordered pair x comma y that's going to be an element of R, which is going to be the relation to our function. And so this whole section we're going to be learning about functions and how the ordered pair is related to a function with the given elements and the domain and the codomain and how they relate to the function. And so this whole entire section is about tying in what we learned from section 1.1 and 1.2 with sets. And so we'll learn right now, so let's get to it. Let A equal the set 1 and 3 and B equal the set of 1, 2, and 3, and define a relation R from A to B as follows. Given any ordered pair x comma y is an element of A cross B. Our ordered pair x comma y is an element in R means that we are given a function x minus y divided by 2. And so the first part of our question says, state explicitly which ordered pairs are in A cross B and which are in B. And so we got to do what we've been doing, which is the Cartesian products, right? And we did that for section 1.2. If you don't remember, I would highly suggest you go watch that video or look up what a Cartesian product is. And so all we're going to do is we're going to have our sets, and then we're going to multiply it out, and then we're going to write out the ordered pairs for that said cross for A cross B. And so we get our Cartesian products, and so this will all be in one big set. That's why it says state explicitly which ordered pairs are in A cross B. So all these ordered pairs are going to be in A cross B, and then we're going to state which ones are part of R, and R is a relation to our function, and we're going to learn about that in a bit. So 3 is 1, and if you know what I'm doing right now, you know that I'm just multiplying 3 times 1, 3 times 2, and 3 times 3, and so that would be our Cartesian product. So right there. So now we identified all our ordered pairs that are in A cross B, but now we want to identify which ones are in R. So now, in order for us to do that, we need to plug it into this given function here. And so let's see, it says means that x minus y is 2. So let's see right here, and it's supposed to say an integer, so sorry about that, is an integer. So we're looking for an integer. So is an integer. So if whatever numbers we plug into this little function here, if it doesn't, it's not an integer, then it's going to not be a part of the relation to our R. So let's plug in our numbers. What's 1 minus 1 is 0, right? And so we're going to write it as following. The order paired 1, 1 is an element of R, which equals 0. And you could write out the whole entire algebra behind it, but this is probably sufficient enough. which is an integer. And so depending how your instructor wants you to explain it, you might want to show all the work right here. This is pretty simple. Okay, so we have that down, and now we go plug in this one in. It says 1 minus 2. So this is all x, right? And this is all y. So, and we're plugging our x and a y right here to this function. And so 1 minus 2 is 1.5. So we get 1.5, which I'm going to put over here. And that's not going to be an integer, so it's not going to be in relation to our A cross B, which is our order pairs and stuff right here. So this is not an integer. And so I'm going to put z for integer, right? Because that's our integer sign. And sometimes the integer sign has these double lines. It's just the same thing. And so now we put 1 minus 3, which gives us negative 2. So this equals negative 1. And so that is an element into relation to our function. And so what is A cross B is? It's A cross B is going to be our sets, right? So this is set A, this is set B. So we're just multiplying our sets to get elements. Those elements turn into our order pairs. Those order pairs are elements in relation to R, and in relation to R is going to be our function. And so this is the whole point of this section. It's trying to make our elements into sets, and our sets into order pairs, and order pairs we're trying to relay that into functions. And so let's see what happens here. This is an integer, so I'll just put it is integer, and this is sufficient enough. If you want to write the little lines right here, then you can. It's the same thing. Alright, 3 to 1, that makes 1. And so that is an element of R. So it is, which is an integer. And so you want to write out kind of a sentence format. So you want to put which is in front of this, which is not, which is. I'm just doing it like this because it will be faster. So 3 minus 2, it's going to be 1/2. And so that is not an integer, right? Because an integer has to be a number that's not a rational in a fraction, right? So what is this? This is not, right? Integer. So there's a lot of ways you could phrase it. And so let's do this one here. 3 times 3. And what's 3 times 3? Let's see. No, it's 3 minus 3, right? That's 0. So let's see, that's not an element of R, which equals 0. So that is not, sorry about saying multiplication, it just is not integer. So which ones are in relation to our R? 1 and 3, 3 and 1, and 1. So that would be our answer. So you state explicitly which order pairs are A cross B, which is going to be all of these order pairs right here, and which are in R. So 1, the Cartesian product give us all these order pairs, and only 3 order pairs are in R. So that's our answer. Alright, so here's our next problem. It says, is 1 in a relationship to 3? So this is going to be our x, and this is going to be our y, right? If you remember earlier from the video, what that means. It simply means this, right? It means the order pair is at an element of R. And so let's take a look at our order pairs over here that we got from doing A cross B, the Cartesian product. So yes, it is. So the answer would be yes. It is a order paired. That's the element of R. So yes, 1, 3 is an order pair that's an element of R. And so now we do this one. You say, we look over here on our order pairs, and we say no. And then you give an answer that looks similar to like this. We're going to say 3, 3 is not an element R. And then we answer this one over here. So now we're going to do the one over here. This one. Is 3 a relationship to 2? And we say our no, because as shown over here when we did the Cartesian product, and if we checked it with in terms of is it an integer, so it's no. We explain why. We show that the order pair of 3, 2 is not an element of R. So, and that's a sufficient answer. So. Alright, so our next question says, what is the domain and the codomain of R? And so we just gotta take a look at our order pairs, right? So we take a look at our order pairs, and then we just gotta determine what is what. And so our domain is gonna be, if it's seen right here, it's gonna be 1 to 3. And remember, the domain's arbitrary point x, and the codomain's arbitrary point y. And so now we take a look over here, and it's clear to see that the codomain is also 1 to 3. The circle relation says define a relation C from R to R as follows: for any ordered paired x, y is an element of R cross R, is an ordered pair of the circle, so this means the circle function means that x squared plus y squared equals 1. And so it's trying to see if we could define this as a circle as a function. And we all know that the circle is not a function, but for the sake of this problem, that's what we're trying to do. And so we're given some order pairs, and we gotta plug it into our set equation. And so 1, 0, what's that give us? Let me pull this one down. So we all know this gives us 1. And so this is going to be, so we just have to say, it says define a relation for any of these, and so you say yes, it is a relation. And you could write it any way you think is suitable. So this is an element of C. So this is what we're trying to define. So let's pull this one down. So now we get this problem. Pull it down over here. So we have 0, 0, which does not equal 1, right? And so this is no, right? Because 0 squared is 0 plus 0 squared is 0, which doesn't equal 1. 0 doesn't equal 1, so no, this order paired 0, 0 is not an element of C. And so now we could explain this next one. So I'll pull this one over here. It says, is negative 1/2, comma, the square root of 3 divided by half a relation to C? Let's see. So now we gotta do some simple math. So we got negative half squared, which is going to give us 1/4. If you're not too sure, you should plug in the points yourself. And 3.5 squared is going to give us 9 on the top, 4 on the bottom. So what's that ends up giving us? So 9 at the top, 4 on the bottom. Which these cancel out actually. That cancels out and it just multiplies on the top. So you actually get 3 over 4, right? Because I'll do just that part of the problem for you guys. Because we got to square with respect to 2 and with respect to 3. And those cancel out, that becomes 4 over, and then that becomes 3. A really basic algebra. And so that does equal it, so we say yes, and we put the order pair, which is going to be -1/2. And you get the gist of it. And like I said, the whole point of this section is to learn why a set and its elements have a relationship to a function. Even though this is not a function, this is just a circle and its equation, but we're getting to there. I keep emphasizing that point for a reason. So now we're going to do the following problem right here. And so this is going to be like this. So -2c is 0. So that just means that's x and that's y. And so we plug in our points and we know that's not our order pair is not a relationship to the function. Let's just say function for now. Let's say play ignorance and think that a circle is a function. We say, oh no, it's not part of our function. So we say no. Right here, no. Our order pair is not an element of C. And then there was this one here. This one actually. So I'll read this one down. And a 0 plus -1 squared, which gives us 1. So yes, 0, the order pair 0, comma, -1 is, what you don't want to put is, but is in means the same thing as saying an element of C. So if you want to put is in, that's alright. So you already got, there's different ways of explaining yourself. So right here we're going to have this last one here. And that one says is 1. So it's just basically saying is 1, comma 1. The order pair are in a relationship with our function C, or equation C. So we plug it into our equation right here. We see that it's 2, which equals 1, so we say no. It's not an element of C. So that's our answer for that. And so our next question is, what are the domain and codomain of C? So seeing that we answered the problem, so now we gotta answer which one's the domain and what's our codomain. And so the domain and codomain of C are both R, the set of all real numbers. Right? Because that's what the question is telling us. We're doing R cross R. And what's R cross R? That's the set of all real numbers. So this is our set. This is our set. And so we just gotta say our domain is R and our codomain is R. And so the last part of this problem says draw a graph for C by plotting the points of C in the Cartesian plane. Well, let's just say this is a good circle. And so that's going to be our function. So that's going to be our answer, right? This is going to be x squared plus y squared equals 1. And so the last part of this would be, is this a function or not a function? This would be my own question. And then you will say, no, this is not a function, because it fails the vertical line test. And if we wanted to plug a number over here, as seen with these order pairs, if I want to plug in x equals 2, then it would not satisfy the two rules for being a function, or two properties, and we're going to go over that right now. Alright, so we're going to figure this out right here. It says symbolic definition: draw an arrow from x to y if and only if x is in relation to y, if and only if the order pair x comma y is an element of R. And so that's just saying the same thing. When we've been working the problems, you probably could tell that this means the same thing. And so let's see right here. We got our two sets right here. A equals the set of 1, 2, and 3. B equals the set of 1, 3, and 5. And define the relations S and T. So we got two different separate relations from A to B as following for all x comma y. And so this is, don't get this confused, this is the definition, right? This is going to be our example. So just in case you guys are a little confused, so our relation is going to be S and T from A to B, so that means A cross B, as following for all x comma y elements A cross B. Let's just say it show right here again. And example 1 is going to be x comma y is that an element of S, means that x is less than y. So it has to satisfy this part of our statement slash premise, and it's asking if the card order pair is part of an element of the S, which is our relation. And so this is how we solve these kind of problems. That's why we just learned the definition right here, the symbolic definition. So we didn't have to, this definition is not that important as the other definitions that I was talking about earlier. So we're going to have to denote a set A, and we're going to have to denote a set B, because that's the two sets we have, right? So now we're going to put our elements into these sets. And what did we learn about domain and codomain? We know that the codomain is our arbitrary y, right? And arbitrary just means it could be whatever you like. In this case, in this situation and examples for this video, we're for the most part just going to use x and y. So this is x, and that's going to be our domain. So it's something we learned back in the day when we were kids. And so that's where we're doing the same thing. We're learning this again, except in a more complicated matter. And not in the sense of complicated, we're learning in the sense that we're learning the definitions of it and understanding how an order pair works as a function and how elements and sets play a role as an order pair. And so let's see here. So I just want to emphasize that an element and a set, that's what these two things, an element and a set, that's what comprises the order pair. And so everything in elements and sets comprise order pairs, and a lot of things in mathematics. So let's continue with the problem. So now we finally drew our two diagrams, domain and codomain, right? And so let's see right here. It says, is x comma y an element of S, means that x is less than y. And so that means this can't be 1, but 1 can be 3, and 1 can be 5. 2 can be 1, 2 can be 3, right? Because 2 is less than 3. 2 is less than 5. And so this is our x, and this is our y, remember? And now let's see right here. We got 3, 3 can't be 3, but 3 can be 5. So what do we know about this now? Well, we just illustrated this problem. We just solved this problem. That's all we have to do. Show it by drawing an arrow from x to y, see? So it's just that easy. So this is going to be our next problem. It says example 2, t equals the set of 2, y, 2, 5. And so we have the set A and B, and this is asking for us to define the relation from t. And so this was, what was this over here? This was the relation for s. Right, we just solved the relation for s. Now we're going to have to solve for the relation of t. And so now we draw another domain, which is going to be a set A. And we're going to draw another set B, right? And feel like free at any time to stop the video or rewind it. If you want to work the problem out yourself, feel free to stop the video and try it. Yeah, let's see right here. So this section in chapter is not as important as, well, these past couple chapters weren't that important. They're more of a foundation, right? They're a foundation to building you up into higher level math. Alright, so if you think you know what to do now, draw the arrow to from set A to set B. And our set A is the domain, and our set B is our codomain. So let's see if you got it right. So we're gonna do 2 to 1. And you probably could guess what the last one's going to be. It's going to be 2 to 5. And it's just as easy as that. So that's going to be our what? Relation t. So we're showing the relation from A to B, which is going to be AT to B. So just same thing as this right here. We're showing the relation from a to x and y like this, or we could say it like this: x comma y, which is order pairs or elements of t. If you didn't understand what this all means right here. So now we're going to do our next problem. Alright, so now we're going to define a function. So a function f from a set A to a set B is a relation with the domain A and its codomain B that satisfies the following two properties. And so these are the two properties that define a function. So for every element x in A, there is an element y in B such that the order pair x comma y is an element of f. For all elements x in A and y in z in B, if the order pair x comma y is an element of f, and the order pair x comma y is an element of f, which is going to be z right here, my bad, then y equals z. And so this is tying in everything we learned from our past two chapters. It's tying in the elements and the sets and putting it all together into what we know as a function. And so this is the standard definition for how to define a set in terms of a function. And so this is what the first property is saying. And so we're going to define property number 1. So we need two separate sets, right? Set A and a set B with their own separate elements. It's going to have elements of y, so let's say 2 and 4. And you could pick any arbitrary elements, and you could pick any arbitrary independent dependent variable. So we're going to have 1 and 2, right? but in this case we're just using x and y, so not to get confused. And so now we define the first part of this. It says for every element x and a, so we have elements x and a, there's an element y and b. So we do. So there's a corresponding element such that x comma y is an element of f. And so let's pair these up. 1 and 2, 2 and 4. And what's that mean? That means we have x comma, or let's define them, right, with our order pairs. So then we have 1 and 2 as an element of f. And then we have 2 and 4, that's an element of f. And so that satisfies our first property. And so what's our last property saying? Property 2 says, for all elements x and a, so we have already this set with given elements in it, and y and z and b. If x comma y is an element of f, so if the order pairs are elements of f, and xz is an element of f, then y equals z. And so let's put another set over here. Let's define the set as 1 and 2 again, and let's define the set over here b 2 and 4 again. Except now we're gonna say this set is going to be the dependent variable z, and we're still going to have this one as the independent variable x. So now we have this, and now they're going to be the same as the one over there. So this is all this is saying. It says for all elements x and a, which is right here, and y and z right here, y and z over there, in b, if x comma y is an element of f, and the elements x and comma z are elements of f, then y equals z. And so what's happening here? These are the same sets with the same given elements. And so all that really means is these two sets are subsets of each other. And remember what a subset means? It means to share the same elements. And it's not a proper subset, it's a subset that contains all the same elements. It's a subset of itself. And so since it's a subset of itself, it contains the same elements. And so this is y and z, and this is x. And so this satisfies property number 2, where it says that for all elements x and a, and y and z and b, so y and z are these two elements. Let's say this is element y and this is element z. Then it satisfies that our order pair is x comma y, and so this is not going to be an order pair. Don't get that confused down here. Our order pair x comma y is an element of the function, and our order pair x comma z is an element of the function. Then y equals z. So I hope you understand these two properties. So like I said, the first property is just really basic, trivial. It just says that there's an element that compares to an element to the next set, and the last one's saying that there's a subset of itself containing that these elements are y and z, so they're both the same elements. So notation: if a and b are sets, so let's say we have a set A and a set B. So these are small sets. I might redraw that one right there. And so we have a set B. And f is a function, right? So now we're defining functions. And like I said, this is the whole point of this chapter. So from A to B, so A cross B, then given any elements of x and A, the unique elements in B that is related to x by f, it's denoted f of x, which is read f of x. So we just define our standard definition of what a function is. Aren't you kind of excited? That's going to be 1 and 2. Let's say 2 and 4 again. We're going to use the same arbitrary elements. So from A to B. So A cross B. Remember what happens when we do A cross B? We multiply every number into each other. So let's make it so you guys understand. So let's say we're going to have 1 and 2. So we have set A. Remember, I have a set A. It's going to be 1 and 2. So I'm just bringing it all the way back. And so you're going to see how this ties in to a function. And then remember we had a set 2 and 4. And so what are we going to do? We're going to do the Cartesian product, which is A cross B. And so what does that give us? That gives us, I'll use a different color right here. This gives us 1 and 2, 1 and 4. It gives us 2 and 2, and 2 and 4. And what's that give us right here? That gives us, if you guessed it, it gives us A cross B, our Cartesian product. And so now it says if A and B are sets, and if f is a function from A to B, which we defined right now, then given any elements in A, which are here, the unique elements in B that is related to x by f is denoted f of x, which is read f of x. So now we just defined what a function is. So let's see. Let's say this is related to that, and that's related to that. And so we got to do the relation, right? And what was the whole point of doing the relation with the r? Remember, it's x and y. It's just our independent dependent variable. We were seeing if this followed the rule for a relation, and so we haven't made any rule for a relation. So if we were to graph this right now, so I'm just going to graph the points. So that's 1 and 2. So x and 2. And we're going to have 1 and 4. So we're going to have a point up there. And you might see why it's really important to see visually what's happening. That's 1 and 2 right here. And that's 2 and 4. And so why do we have these properties? Remember the two properties we learned? But let's say 1 and 2 and 2 and 4 define our function. 1 and 2 and 2 and 4. Right, that defines our function. And let's say our function is going to be f of x of, I can't think of something right now, but let's say it's a function. That means these don't satisfy the relationship to r. And the reason why we have our properties are because, remember, we can't have 1 to 2 and 1 to 4, like you can see right here. Because then that, like I said earlier, breaks the asymptote for what we learned from algebra. That doesn't define a function, and we can't have something that goes away against right here again, the asymptote again. So pretty easy. If you understand what's going on now, I hope you do, because we're about to do an example right now that's pretty similar to what we just did. And so right here we're going to have three functions. It says squaring function, f from r to r, is defined by the formula x squared. We have the successor function. And so these are really important functions. And I want you to remember this. People use it in higher maths, and everyone uses these in higher maths in terms of knowing the definition of what is what. And so this is our successor function. You just need to remember this. And this is our constant function. And so this is a rational number 2. So it's going to be r, or actually q, right? Because q stands for rational, cross an integer, and that defines a constant. And two integers define this, and all the real numbers define x squared. So that's pretty basic. So if you wanted to take note of that, something to take note. It's not really mandatory. So now we're going to have this example here. It says the circle relation C was defined as follows. For all order pairs x comma y is in R cross R, x comma y, the order pair, is in C, the function, means that x squared plus y squared equals 1, which is going to be our said function. Is C a function? If it is, find C sub 0 and C sub 1. So the big question I've been asking the whole entire video, or all these problems and examples we've been doing, is it a function? So let's see here. So what do we know about a circle? Right? We know that it's not a function. So the following function doesn't satisfy our property 1 and 2. And so the best way to see that, remember, is to always to visualize it. So let's say we have a circle, probably not the best circle here, but it's a circle nonetheless. So let's say that's a circle centered at 0. So what was our first property, if you remember? So let's define it. Let's see. There are many real numbers x such that x comma y are not elements of C for any y. And so let me write that out for you. And let me type it out first and I'll write some stuff. So there are many real numbers x such that x comma y, which is going to be our order paired, is not an element of C. So it's not an element of our said function for any y. And so what's that mean for us? There are many real numbers x. So let's say we have x right here. Is that a part of our function? No, right? Because it has to be along this curve, right? This is the circle has this curve going around it. Is it right here? No. Out here? Let's say 2. So I'll say x is 2, right? This is x equals 2. And so if we plug in that into our function here, what's that give us? 2 squared, which is going to be 4, plus y squared, which equals 1. And so you already know it's not going to be part of this. Just by looking at the graph too, you know it's not part of it. But let's say for the sake of this, we subtract y squared equals 1. It's going to give us negative 3. And so what do we know? There's no real number y, so that this following part of the said function is true. And so this is not any case for any real number y. So, right, this is not true for real number y. Because what happens if we had to root this? It's going to give us an imaginary number, right? That becomes 3i, and and it just doesn't look good for us. So this is not true for real numbers. That's why it explicitly says right here real numbers. So we can't work with imaginary numbers. So it breaks property number 1, right? And if you don't remember what property number 1 was, we used these sets. We had 2 sets, so I'll show you again. We denoted them 1 and 2, and then we said we denoted set B 2 and 4, and we said that if there's a point or element that's contained in X, there's a element contained in X which is going to be the set A, right? This is X, this is Y. Said that there is always something over here for said X, and so we said in this case, right? So I'm gonna erase this. Hopefully this clarifies. You know, there's might be a little confusing trying to wrap your head around it. But we said in this set we have 2. And there's no corresponding number that connects with this 2. So I'll put a question mark. There's no number that connects to that 2. And so this doesn't define the property number 1. And this doesn't define the property number 2. And what was our property number 2? Remember, if you remember our property number 2, we said y and z can equal each other. And so let's take a look right here. Let's say we have this point right here. Let me erase some of this right here so you don't get confused. So this circle has a radius of 1, so don't get confused with these numbers right here, these little lines. These lines are just trying to like show you what I was trying to mean. Like, we can't have an x just right here or an x out there for the function because it has to follow along the curve. And so let's do what we did last time, remember? Let's say we have a vertical asymptote, and we learned this in algebra. It's a classic way of defining a function. And so what did we know? So what's the first thing we could say about this? There are 2 distinct values of y, so that x comma y is an element of C. So if we make a vertical line, it might be more clear to see right here. Thus C is not a function, right? And why is that? What's that mean when I said there are 2 distinct values of y? So let's say I have this point right here and this point right here. This would give us this for this portion of the curve, and this would give us this for this portion of the curve, this chosen point for these chosen ordered pairs. And so what do we know from seeing this? There's 2 distinct values for y right here. 1 value for y, 2 values for y. And so that goes against our rule number 2, because remember what it said? It said y has to equal z. So that means the values have to equal each other. We can't have, let's say, 3.5 equals negative 3.5. And so that was our property number 2. And this was our property number 1, right? That our element has to connect to an element over here. In this case, there was no chosen element for y. Distinct element that follows along the curve. So, and I hope you understand what's going on now, right? So this is property number 1, and this was property number 2. And so if you want to go back and watch the video again. I highly suggest it, so you can understand what's going on now that we solved this. So this is going to be our last problem. It says to find f r cross r and g r cross r. So these arrows just mean finding the Cartesian product by following the formulas. So we got two formulas. F of x equals the absolute value of x for all x elements of r, and g of x, which equals the square root over the square root of x squared for all x elements r. So does f equal g? And so let's plug in our numbers for said x to see our output of y. And so what's the absolute value of 1? It's going to be 1 to 1, right? What happens if we put 1 into here? That's going to be 1. Square root of 1, that's going to be 1 right here. Let's plug in negative 1. So we plug in negative 1. And that gives us 1. And negative 1 right here gives us 1 to 1, yeah. So if we have a little number chart or graph, because we're dealing with x and y, we're going to have a 0 right here as our point. Let me get another color. 0, 1 and 1, negative 1 to 1. And what we know about absolute values, we know that the function goes like this. And so does our function of g of x. And so this function right here, does f equal g? So we say yes, f equals g. And you could explain why, depending on what the question is asking us. And so the question is that we just gotta say yes, f equals g for our given functions, because of the r cross r gives us the ability to choose any order pairs as needed for the given function. So this is what I just said. I said r cross r gives us any order pairs needed for our functions f and g. And f and g have, and f and g say the same thing. Or you could say f and g equal each other, and f and g equal each other. And you have to write it a little more prettier. I just wanted to show you how to say it. So that will be our answer. So thank you for watching this video. If you like this video, please like it and subscribe to my channel. It will help me to keep making videos like this. If you want to see more videos like this, please leave a comment down below and say that you want to see more content like this. And if you want to see something specific or something else, please leave a comment down below too. Thanks for everything, guys, for watching the video, and I can't wait to see you guys next time. Bye.